Hello, this is the next video in a playlist that I'm calling Transformations of Random Variables. And this is part 2, where we look at taking two normal random variables and transforming them to a Rayleigh distribution, a Rayleigh random variable. Now in part 1 we used one method, in part 2 we're going to use two different methods. And so the first one is, if we let yi equal, first of all we let xi equal IID, normal random variables, mean zero, constant variance sigma squared, common variance I equals 1 to 2. So we have x1 and x2. Let yi be xi over sigma. Then this is a standard normal, right? If we subtract the mean, which is 0, divide by the standard deviation, we get a standard normal random variable. And this is for both I. So we have y1 and y2. Now if we square the y, so yi squared, call it w, then w follows a chi-squared distribution with 1 degrees of freedom. And they're independent, right? The x's are independent, the y's are independent, the w's are independent. So we have two independent chi-squareds with 1 degrees of freedom random variables. Let's let t equal w1 plus w2. Then if you sum independent random variables, you add the degrees of freedom. So t is a chi-square distribution with 2 degrees of freedom. If we take the square root of t, then that, and call it z, then z becomes a chi distribution with 2 degrees of freedom. And as a reminder, a chi distribution with 2 degrees of freedom would be this. F of z is z equal to x, e raised to the minus z squared over 2. Now if we multiply z by sigma, call it s, and then here we have, so let's find that using the variable transformation technique. So we solve for z, take the derivatives, then this is the Jacobian. So f of s is f of z, but we plug in this piece into z, and we take the absolute value of the Jacobian, which is 1 over sigma. Now z, so if we plug in this for z, we get s over sigma, but then this extra sigma here makes it sigma squared. And then and we have e raised to the, and if you plug in this for z, you get minus s squared over 2 sigma squared, which is the Rayleigh distribution. So we've taken standard normals and transformed them to a Rayleigh distribution. Now, why is this? So if we look at sigma z, so s is sigma z, but z was the square root of t, and t was the sum of w1 and w2, but w1 and w2 were y1 squared plus y2 squared, but these y's were x1 squared over sigma squared plus x2 squared over sigma squared. Well, this sigma, if you bring it in, cancels with those, and we're left with the square root of x1 squared plus x2 squared. And this is what's commonly used to transform to a Rayleigh distribution. Now the second method is, I call it the Cd Cdf method. So let's let y equal this quantity, square root of x1 squared plus x2 squared. And a note, if we can find the CDF for y, take its derivative, then we get the density. So let's look at the CDF, f of y, which is our random variable, less than or equal to some quantity. But y is this, and next we will use Lotus, and it's called the law of the unconscious statistician. And I actually have a couple of videos on Lotus that, even though you think we should use the distribute, remember f of, the CDF is probability, so we're trying to find this probability that this random variable is less than this quantity. And so you kind of think that we should use the distribution or the density for y. But since it's a function of other random variables, Lotus says we could just use those densities right? So x1 is a normal random variable, x2 is a normal random variable. So let's use that. And so to find this probability, well, this is a circle, you know, being less than y, and we have to take it times the bivariate normal distribution, you know, but they're independent, so it's just the product of their respective marginals, and this is it. So this would be the CDF, and then we take the derivative of it. So on the next page, we'll fill in these pieces here, right? So this is the standard normal. Remember, we're still integrating over the disk, or that circle, and this is the standard normal for x2, dx1 dx2. Now let's convert the polar coordinates. So let's let x1 be r cosine of theta, x2 times r sine of theta, and the Jacobian of this is you take the x1 times the derivative, derivative with respect to r, and we get this. Derivative with respect to theta, we get this. Derivative with respect to r, derivative with respect to theta. And this determinant, so you get r cosine squared plus r sine squared. R can be factored out, and then you get cosine squared plus sine squared, which is 1. So that's why we get r. Now, here is the density. So the angle of that disk goes from 0 to pi, and the length goes from 0 to 1. So that's how we're integrating over the disk in polar coordinates. So x squared, we plug in this and we get, r squared cosine squared, and here we get r squared sine squared. The r squared can be factored out, the other's 1, so we get this from the exponents, and then we have to add those to this. And don't forget the Jacobian. D theta dr. There is no theta here, so this piece can be moved out, and we're just integrating 1, and then the antiderivative of 1 is theta, plug in 2 pi minus 0, we just get 2 pi, and that 2 pi cancels with this. That's why we're here. Now this is the CDF for y, okay, and we're going to leave it like this because taking the derivative, when you go from 0 to y and you take the derivative with respect to y, then it becomes easy. So the density of y is the derivative of this CDF, but the fundamental theorem of calculus says that if you take the derivative with respect to y, it says you plug in y for that random variable, and that's what you get. And that's the density of a Rayleigh distribution. Well, that's all I have for part 2 of this. I think the next video I'll calculate the mean and the variance, the median, the CDF of a Rayleigh, and post that. Thanks a lot. Please like the video. Subscribe so you don't miss the next one. Thanks. Bye.